Okay, so welcome to our last network security lecture. Today we will look into secure software development. It's not so network related, but I think this is some kind of core element that we should also discuss. And basically we will discuss three elements. So if we look at software development at the software security development lifecycle, how to create secure code, there are several steps involved. Obviously, you need some training for people involved in software development. Then you have to define the requirements. Then you design the system, you implement the system, you verify the system, then you release it, and if something happens, there's a response element. What we will look into today is where you can basically how to build secure network systems. So what you should look for. Where should we start? So this kind of guideline, I mean, this is just some kind of categorization of the steps defining a process that's involved in software development. And that's for Microsoft. There are other descriptions, other kind of categorizations. The steps are at the end always the same. So first of all, with requirements, there are several requirements tools, such as from governments, such as from BSI, German Department for Security and IT Systems. There's also from National Information Security Society. So there are for different kind of governmental recommendations. There are some kind of recommendations, policies defined also by companies, security by design. So for example, that you always need to maintain and keep an eye on the security elements. There are legal requirements such as the aim for privacy and handling as personally identifiable information delicately, as we have discussed. So let's say you get some kind of requirements up front. So you need to first be aware what you want to build, what kind of data you will deal with, what kind of tech models there might be. And with that in mind, you typically start to design your system. Especially when it's a distributed system, you have several attack surfaces, you have several services interacting with each other. And then typically threat modeling is a common way to first identify what further requirements you will have in implementation. So the requirements will define obviously the requirements for the implementation, and in your design you do it at a higher level as well, and then you get a quite long to-do list what your system will look like and what kind of security mechanisms you should implement. And the idea why upfront in these kind of requirements and also through threat modeling you identify what kind of countermeasures you have to implement, the idea is the earlier in the process of software development, especially for networked systems, you identify some vulnerabilities, some weaknesses, something that you need to address, the less effort you have to deal with it. So on the contrary, once you have implemented the system and you are already in the release phase or verification phase and some kind of issue comes up, then you have to revise your design, you have to re-implement several aspects of your code, of your system, and then it's much more work, and even more work it is when the system is already out and you have to take care for backwards compatibility, and you are even have to have a look at that. So the earlier you address the security issues, the better. So therefore we look first at threat modeling, what this is, especially if you build distributed systems where you have, let's say, a database, you have a front end somewhere on a web server, you have a web server, you have some client, you have maybe some other logic on other machines that have to communicate. So you also need to keep in mind that these services are available through network. And threat modeling comes in at that place that allows you, using a tool, to basically sketch your system and to learn what kind of weaknesses it has and what kind of countermeasures you should account for. So what is threat modeling? So you draw typically a system model, like here, with some kind of pictures, with some kind of model elements, which service should interact with which other service. And yeah, and typically if you have a larger system, then you have quite a lot of components, lots of communication going on. And what you want as an outcome is to identify the potential vulnerabilities for this system that you sketched out, so that you can derive mandatory security concepts as countermeasure, so that when you start implementing, you already know what you will have to implement as a countermeasure, and then you implement only once. So basically, you build a system model, and for all of these components and the communications, there's a threat library matched to it. This is just an example. I don't know. I mean, there's quite many weaknesses listed. I don't know, improper restriction on operations within the bounds of memory buffer. So if you use a database, you have to implement. We'll have an example for that. So the aim is to have as early as possible in the design phase this kind of step, so that you already can foresee what vulnerabilities might come, what weaknesses should be addressed, so that you save later the effort. Okay, and for this purpose, there are quite only a few threat modeling tools available. So we will have a look at one threat modeling tool. This is, for example, the one from Microsoft, where you have here typical how it looks like. You have here various drag and drop options that you can drag into the user interface. You can sketch the communication patterns. You can sketch some boundaries, which is trusted, what's not trusted, and so on. And then you get as a result some kind of guideline, some kind of, for every step, every interaction, every module that you specified in your system design, you get a list of potential weaknesses, so that you give also a guideline what you should do. Ensure that only specific trusted origins are allowed for gaining access to the code repository, for example. So there are only a few tools available, let's say 10. Not much more. So there are some diagram-based tools, as you see here, that you can drag and drop, as in Visio or in PowerPoint, the corresponding elements. That's Microsoft Threat Modeling Tool, OVA's Threat Dragon, OVVL, that was a bachelor thesis, product resulting from bachelor thesis, and I think master thesis afterwards. There are some commercial ones, Serious Risk, SecuriCAD, Threat Modeler, and that's almost it with regard to the graphical user interfaces. Then there are also some kind of text-based tools where you can not verbally, I mean, you have a clear syntax how you specify these kind of interactions. I mean, this is not, if you look at this example, we will have a look into it. But if you look at these are just building blocks. You say, I'm using a database that you can also do via text file. And then you say, my database interacts with the front end, let's say. This can also be represented by text. Just say, there's a link between database and front end. I mean, this is not too complex. So there are also some text-based tools like OVA's PyTM or Fragile. Yeah, there are also some other ones, but that's it. That's the complete list of available threat modeling tools. Let's have a look at Serious Risk, for example, how this looks like. So here on the left, it's a little bit hard to see, but basically here you have specific nodes where you can drag and drop into your system, and then you can draw some arrows in which data is flowing, and basically this is all what you do. Let's have a look. So I will start the Microsoft Threat Modeling tool. Where is it? Here it is. This is how it looks like. We can create a new model. Here we can select where the nodes come from, so what kind of knowledge base they have. We just take the regular one, create a model, And then let's say, what do we have? We have a web server. We have, I don't know, a browser interacting with the web server. Then we need a database for, let's say, it's a human user. What else do we have? A SQL database. I don't know, what do we else? Generic data flow, HTTP. Like this. Then we have some kind of, this is a generic trust boundary, let's say. One moment. So this is the boundary. I trust that my web server and my, just think of it as being drawn nicely. So this is somehow trusted. Here's some internet. I don't know. So we can basically drag and drop our element here. What else? Maybe there's also some kind of web service that the web server uses, and then we define the web service is using some HTTPS connection. So you see, it's not too complex. Okay, we also need some kind of communication with the database. So you draw your big system design, and then you go to reports, create full report, generate report, then we save it somewhere, desktop, report, and this is our report that we got for this thread, for this design. And basically it tells we have following interaction. One moment. So for example, web server and SQL server, there's the problem of spoofing of destination data, store SQL database. SQL database might be spoofed by an attacker, and this may lead to data being written to the attacker's target instead of the SQL database of the web server's writing to the database. An attacker could claim to be the database, and it is not, and the data from the web server entered by the user is written to the attacker's device and not in the database. So we should consider using a standard authentication mechanism. If we write data into the database, there might be a SQL injection vulnerability, so we should take care that any procedure that constructs SQL statements should be reviewed for injection vulnerabilities. I mean, as you see, either for the interactions, for this data flow, this HTTPS also, therefore we get some kind of response, or sometimes also for the devices themselves. It's a little bit, actually I was assuming that there should be much more for the web server, for the web service. We just have 5 recommendations. I think I've missed some of the elements, what interactions could happen. But basically this is the outcome that we have. And as you might not see, but what is working under the hood is that basically for all of these interactions, for accessing the database, for accessing a web service, for the web server itself, for the SQL database itself, there is this kind of text somewhere in the thread library embedded. So some people, the developer of the thread modeling tool, have selected this statement to be presented if you want to write into a database. And every time you write into a database, this specific text pops up. It's really a very simple, hard-wired link. So if you took a writing process into the database, this should be presented. And for all other components that we have, that you can select here, there's basically a text associated to it that will be displayed once you select that specific node or once you interact with that node. So it really depends on the quality of the thread library, what kind of text is associated to file system, to database, to web server, because this is, if you select it, you are presented as text. So this is how it looks like. So at that setup, I had 175 recommendations. You see the system artifact, you see the vulnerability, Sometimes it also recommends the mitigation, what you should do. Only specific trusted origins are allowed. And that's basically hardwired to the node that you have selected. So the point is, these tools are as helpful as complete their threat library is. So if they have a full threat library with very many vulnerabilities known and useful countermeasures, then you get a long list with a clear to-do list, basically what you should do. So in this example, there are several mitigations also listed that you should take into account while implementing. And if you would have a threat library which is quite small, has incomplete list of vulnerabilities, then you still get some recommendations, but they are limited in their use. So what we found is, in the core there's a threat library. It's hard-coded. Basically, every artifact are associated to an element of the design, so this is what you can select. There are vulnerabilities associated to these artifacts, and there are countermeasures listed to these vulnerabilities. So this is basically very simple. And as an output, you get this result as a report, where basically all the vulnerabilities to the nodes, to the system elements that you selected, artifacts you selected, are listed, and the interactions that you selected. Here's a, maybe for the classification again, I mean, here we had this several tools, the diagram-based ones and text-based. How would a similar setup look like in a text-based representation? Like this, that you define the nodes. DB is a data store of type SQL database. It has the operating system CentOS. There are some further information that will enable or disable some elements in the report. And this is how you would define it as a text-based. And a diagram-based, you have this drag-and-drop elements. And the threat modeling libraries look typically like this. Sometimes some of the tools also support that you can modify and extend them by your own, so that you can add further vulnerabilities and further text elements that will pop up when you select a specific node. Okay. So just to say, where are these information for the threat library coming from? So typically, there are public databases, knowledge bases on products, on weaknesses, and on vulnerabilities. So at the time, I think this is from 2023, now there's a list, there's common platform enumeration. This is publicly available. We can also look it up. I mean, CPE, hopefully there's now products. Okay, common platform enumeration. Okay, good. So this is the dictionary. You can look it up. There probably now there will be it's still 2000. So how many do we have now? So you can download it. I think now there will be roughly 900,000 products listed. I don't know. If you look into it, any idea? Debian, maybe. And then we get probably 10,000 entries. No, 2,000 entries, okay. So basically all of these products that are available and listed. So you have here the product, and you have the associated vulnerabilities known to the product. So this is the product, this is the component, vendor, Debian, product, adequate. There's some changelog. You can look at the vulnerabilities. Okay, so now we don't have vulnerabilities for this product, but maybe to take an older one. So this version 0.1. Do we have some vulnerabilities there? Yes. So before version 0.81, when run with by root with the user option, allows local users to hijack the terminal and possibly gain privileges. And this is the second database that we have, the vulnerability database, so common vulnerability enumeration. It basically lists for what product it is associated. It tells also what the issue is, typically. Typically it should list that. Yeah. Okay. So basically it's then described what's happening, yeah, and how it can be how it can be done, what kind of issue occurred. So basically this is the second element. So we have the platform enumeration, where we have, I think now it's 900,000 products developed. I mean, it's continuously developed. You can register your product if you have a new software. That it's just some kind of enumeration so that people can refer to it by a common unique identifier. And you can be very specific. As you have seen, they are also listing the different versions. And you can also ask the vulnerabilities associated to this specific product. Just as a note, there are 700,000, 900,000 products. Typically in the tools you find only 100, such as MySQL. That's it. And this Debian adequate will not be present, probably. So, and then to these products, there are roughly 150, maybe now 170,000 vulnerabilities listed. And they contain the basic information, what is the issue, what can happen. Some have been fixed. I mean, some can also list how the countermeasure is. And typically in these tools, this is the threat library. Basically, it lists, if you have selected MySQL, then you have a specific vulnerability. And these have been typically by the company providing the tool handpicked and embedded so that people can make use of the tool. And because you have so many vulnerabilities, there is some kind of categorization. So all authentication issues are subsumed under very generic weaknesses. So the weakness would be authentication issue or privilege escalation. And the vulnerability itself is the specific one for that specific program, how it behaves. Sometimes they also have generic countermeasures. So if in order to avoid privilege escalation, you need to introduce some two-factor authentication, for example. So and basically this is the threat library. So it lists for the various artifacts, so selected ones, MySQL, Debian, such, a list of common vulnerabilities and some countermeasures. And this is what is given in the report based on what kind of system artifact you have selected. So, to summarize, in threat modeling we have these two types, diagram-based, with the drag and drop, and text-based. They can do the same, so it's yes, the text-based might be a little bit more cumbersome because you have to know what kind of databases they are existing. You don't see it, you cannot drag and drop, but sometimes you can also configure it a little bit more deeper. In the diagram base, you would maybe have to right-click, edit properties, define that it's hardened or not. Yeah, I mean, obviously this is more user-friendly, but the text is easier to extend to script, to import, export, to integrate in other programs. So it has also benefits. Okay, and then the question is finally the threat library quality. So many free tools come with a very basic, simple library where basically so an open source free tool with less manpower behind it, typically they list only one database, and there you have only 2, 3, 4 potential vulnerabilities. I don't know, password protected, make sure that people don't gain access to the machine and so on. And commercial tools that put manpower into it, I don't want to make advertisements or so, but typically they live from the effort they put into the threat libraries. So let's say if they have some automotive focused threat library which knows what happens in the automotive world, what kind of components are used, and then really put effort into keeping them up to date, putting more and more vulnerabilities inside, and countermeasures that really guide you through how you have to counteract, what you should implement, what kind of settings you should change, and so on. So typically this is where they make their money, by selling the access to this sophisticated threat library. So they are really quite helpful sometimes, so that it guides you through how you have to configure your MySQL database so that you really avoid privilege escalation, while the simpler ones just tell you to do so, but not how. But in general, this is quite useful, nevertheless. So if you plan to set up some distributed system, then just use the tools up front, and then you can get some core idea of what to-dos you have to secure your system. Okay, we did also one paper on this. So basically at that time we compared what tools there are and selected some of them. And just to highlight what the conclusion of that paper is really that the quality of the threat library, that's the essential one. So of course with simpler ones you get also results, it helps you to get into identifying your issues, but with the more sophisticated one you get more information, obviously. And at the end, if it's diagram or text-based, it depends on how you want to use it. If you want to integrate it in some kind of text processing into other tools, then text-based tools are useful. If you use some diagram, that's more user-friendly. And sometimes they also support some questionnaires. So sometimes they also guide you through the process. So you select the MySQL database, for example, that you want to embed in your system, and it asks you which version it has. It asks you how many users should interact with the database, how you plan to use it, and then it gives you different recommendations based off that. Maybe what else to say here? Yeah, the threat library. That's maybe again the focus. So Microsoft has just, let's say, 50 elements, 50 items you can select. The text base has, let's say, 100. The commercial ones has 200 elements that you can select for your system. There are different kind of sources where the vulnerabilities come from. Yeah, at the end, it's recommended to use, and that's one first step. Okay, so let's say we have achieved the first step. We know now we have passed this barrier. We know now what we want to implement. We have a system design. We have sketched the elements that our system will have. We have learned what kind of vulnerabilities to look for, and now we go into the implementation mode. And now we look into this aspect: deprecated unsafe functions and static analysis. So now you want to build your network system. You start with the first class. You start with implementing, and typically out there's the knowledge in vulnerability databases, maybe which kind of functions have problems. I don't know, typical example is for buffer overflow. If you allocate some memory and you read user input and assume that the user input has a specific size, but it does not have that size, it's bigger, then it writes into your memory and overwrites your jump back address and so on. So you would like to get some support for secure implementation during your implementation. And this is where the next point comes into play. Okay, so basically what they came up to is that previously, so you started coding, and then maybe a second person looked into it, manual code inspection. Yeah, that works when people, the team is small, everybody knows what the others are doing. When they can think into the system themselves, you know your colleague is working on this specific function. When you look into it, you know the purpose of the function, you know how it's embedded in the whole system. You can verify maybe, and as a second person, identify some issues. But the problem is, the bigger the system gets and the more people get involved, it will become impossible to overlook the implications of the whole system when you're working on a specific function, let's say. So next step on Microsoft approach was to have lots of unit testing. But I mean, that is also a common next step. So basically, because you don't know what all implications there will be, you write a lot of unit tests that basically you can run every time you checked in some code, and it verifies that everything still runs as normal. But you can only test for what you know. Yeah? If you write the tests, it will detect the issues that you specified as an issue. Yeah? And basically, what is the next recommendation is to add static analysis that, in addition to a human person checking the code, checks your code as well. So what does this say, and what is the idea? So basically what they had is quite large projects, and they identified that if they add some kind of tool-supported security detection in the code, they could reduce the effort for finding issues. Obviously, I mean, if you have some tool support, then you get supported and you reduce the time, obviously. It's like writing in Word and you have a spell checker, and if the spell checker tells you this word looks strange, then you can focus more on the words that are highlighted than in generic, where you might overlook it. So the idea is to have some kind of highlighting, some error highlighting for code that we are using also in Word for text spell checking, to have something similar also with code. And basically there are two categories here, what you can do. So one is the static analysis, where you actually you don't execute the code. It's like really a word highlighting, spell check highlighting. It follows the abstraction. It finds bugs or enforce specific correctness. So that means, let's say again the example, you want to read input from the user. You allocate some memory for it. Then that part will be highlighted. You allocate your data memory, and this is the point where you when you enter data into this memory, and you haven't used an unprotected kind of read mechanism from the user input, so that it doesn't guarantee that the size is valid, so as expected. So therefore, you don't have to run the code. You just check what kind of functions are used. You check for which functions some security issues are known, and then you highlight it to the user so that the user can react. So this is the static analysis, not running. And then there's dynamic analysis, where you basically execute the program, yeah, and then you analyze the execution, how it interacts with the memory, how it interacts with the CPU. And basically you give it a specific time, yeah, I don't know, you give it, 20 minutes. And then in that time you verify what kind of calls it executes, what kind of memory interactions it has. And after 20 minutes, if you didn't find anything, then you say, nah, okay, we didn't find anything. So it's often memory related, performance related, concurrency, security related. It helps to find bugs, to profile your code, and to enforce some kind of, stronger specification. So if you detect that the CPU consumption is out of bounds to what you expected, or the memory consumption, then you can identify, okay, that you made some mistake, and you can correct it. I don't know, if you have some faulty recursive function that is allocating more and more memory, then it will be detected, which is not the case here. So let's say if you have here some recursive function that it's like maybe this, I don't know, start, allocate memory, and then return to start. This you will not detect in the static analysis, but you will detect in the dynamic analysis. So, and let's see what is the benefit of it, then we will have see some examples. So basically what the conclusion is, that these are still old studies, because since then it has been some very common tool to use. So basically they found out that with static analysis the productivity grows and it affects per kilo lines of code, so 1,000 lines of code is reduced. So obviously it is helpful. You gain some statistical, some quality. Just to show you some codes, some kind of examples in that context. So let's look at some static analyzers. So our goal is to have static analyzers to measure the code quality and the code security. The aim should be clean as you code. So you should, when you code, you should result in clean code, which is security aware. And if there are some issues, it should be highlighted to you. Yeah, there are some tools for it, such as Clockwork, PyCharm, or C-Line, and SonarQube. So they are focusing on specific languages. I mean, obviously, you have to focus on specific language if that will be some code highlighting. As a spell checker in Word, this is a spell checker for your coding. So it needs to be aware of what kind of functions are offered in C and in Java, for example, for which of these functions some vulnerabilities are known, and that you can get highlighted some kind of issues then. So also, okay, this does not support Python and JavaScript. This locate that's code, find probable bugs, spelling problems, but limited to code issues only, so less system to system. SonarQube is more versatile, that we will talk about now, but of course there are many tools that you can look into. Just want to show you the example that you have seen it once. Okay, so what is the idea? So now we want to motivate for basically clean as code, and clean as code means that once you write code, you want to leave it in a state that there's no need for somebody to look into it, to touch it. So basically the depth, the technical depth for it should be zero, it should be up to date, it should be verified, it should be somehow secure. And why is that idea relevant? Because let's say you write some code, it's working, but somebody still needs to look at it. Let's say it has a depth of, I don't know, 10 hours, somebody needs to look into. The next time you write, then it's 10 hours again. And actually it would take then longer, because people would need their working time to reduce your technical depth to zero, to invest time, to identify bugs in your code. You need either more team members or the same people but in less time, so more time pressure. If you always have to check old code, that's less motivated, so you have more conflict. So having a high depth leads to more depth, because the people are constantly working on previous elements that they are not highly motivated to do so. So the goal is to have some depth-free code. Basically, that it's not really required that somebody else looks into it, because some of the common elements that would somebody else need to do have already been done. So what can be all in this code? So what should we look for? And typically you have some issues. You can have null pointer, so pointers pointing nowhere. You have allocated memory, you have freed the memory, but then you access it again. You have freed it again. I mean, that would mean to delete what has been stored at that position, although you are not anymore responsible for it. Array indexing, so if you access an array outside of its bounds, typically, yeah, that these are errors, or stack overrun, heap overrun. Or your return pointer in your function is modifiable by the code itself. That should also not be happening. Uninitialized variables, I also get several times in Python when I'm using it. Invalid use of negative numbers. I mean, these are all elements that you are also aware of what can happen. Passing large parameters by value. So if you hand over as a parameter, I don't know, a very large number instead of just referencing the memory where it lies. If you have dynamic data, such as reading from a user input and you didn't associate sufficient memory to it, memory leaks, file handle leaks, I mean, that means that file memory and network access is available probably to spaces that are not belong to your code, unused values, unhandled return codes, and so on. So there are many elements that could happen while coding, and let's say an experienced programmer might detect and think of these issues when he sees the code, but it depends also how much time is available, how quickly the person needs to look through the code, and obviously there are some issues where it might be overlooked. So the question is, wouldn't it be nice to have some highlights, some kind of tool support to identify such issues? This is where SonarQube comes into play, and this is also maybe the most important slide with regard to static code analysis. So let's say it's a web tool, it runs on your code, it doesn't need to execute it, and it finds issues like bugs, security vulnerabilities, code smells, there's an L missing, code coverage, duplications, supports lots of languages, and this is how it looks like. It's highlighted in red if there's something, and you get the tooltip telling you what issue is there. So the null pointer exception can be thrown, provided class is nullable here. So it has not been defined up front because the class has been, this example provided class is defined in if clause. So if it's not entering the if clause, then you have no class associated, no object associated, and then you might have a null pointer exception here. So it's really as the spell checking in Word and Word programs, writing programs, it's the same for code. So it needs to know the code, it needs to know what kind of, what potential code flow might be. So what it basically checks is if this if clause is not entered, then I have here a class that has not been initialized, then I get a null pointer exception. But it might also know for different functions, for example, which if you read from the user input, it might recommend you to use a function that limits how many characters you read, so that you never get the case that you got more data that you want to put in your memory. So it's a simple highlighting tool for your code. It doesn't need to run the code, it just can simply check what might happen, and then it basically computes for you where you have to do something, code smells where you should look into it, and depth, how much time you need to invest in order to resolve it. And then you can basically define for your depth how much time should be acceptable for a class or code that you, let's say, checked in, and only if it does not surpass 10 minutes, then it should be accepted. Otherwise, you should revise it until this highlighting is reduced, and the number of depth, the minutes that you need to invest is reduced to an acceptable number. Okay. Yeah, it supports 29 languages. I mean, yeah, this is a web-based tool. Typically, it integrates with your Git repository so that it can run on your code. It has 4,800 predefined static analysis tools, basically knowing for the various programming languages what it should recommend. You can also add your own rules. This is how a rule looks like. Variables should not be self-assigned. There's no reason to reassign a variable to itself. So either the statement is redundant or should be removed, and the reassigned is the mistake. So what is non-compliant? A function set name equals name, and you should use this kind of approach. So basically every time you see somewhere name equals name, then it should get the hint that you should use this, so that you clearly separate between the local variable and the global variable and so on, so that it's more clear what is implemented. Very simple. Again, in this kind of security support, it's always very simple. Depending on what you enter, so in this terms, your code, it checks for different patterns, and then it tells you, this is some issue, please correct it. Okay. Okay, so, and the idea is of course, so let's say you have, basically, and then while you are coding, then during your coding, it is highlighting and it's checking what you entered newly. So it focuses on new code, it focuses on the current code that you're writing on, and this associates the quality of the code to the developer, so that the developers can also see how much depth they create, and they're motivated to reduce that depth. And once, let's say, they check it in, then you can also automatically assign an issue to a developer to please check here the code. Somebody checked in. It has this and this points where it needs to be revised. Can also give you recommendations how to recreate it, what you need to correct. So it helps you in developing your distributed system. This is how it looks like. So for example, it has here different projects which tells with regard to bugs, vulnerabilities, hotspots which need to be reviewed, code smells, and it can run for, it runs on the Git repository, so it has access to it and can give you that information, and it can also be integrated into your user interface that you use for coding to give you, during your coding, basically the feedback. So how does this look like? How do you create a project? You need to associate it. So first you create, SonarQube is a web-based tool, so it runs on a web server. It is a service that user interface runs on a web server. And then you associate where the data, which repository it should be associated to, such as GitLab, Bitbucket, or locally. You define the properties that it should be able to run. You select the programming language, and then basically it tells you for your code what kind of property it has. In this case, 2 days and 5 hours are in depth. 2 security hotspots, 33% has been reviewed, 167 code smells, almost 1% duplications on 17,000 lines of code. So you have a clear guideline where you should look into in order to use your valuable time for reviewing on parts that have already been selected. So, what is some kind of code smell? Just to show you some examples. A code smell is technically correct, but it might be confusing. Yeah. So, for example, if not this and this, and then a second if not, then you could merge it into one if statement to make it more clear that there's no alternative. So, the code that is somewhere here as a next line coming is only executed if both triggers, both factors, both clauses are negative. So, if instead of having 2 if conditions, you should combine them in order to make it more readable. Both are technically the same. There are no difference in kind of security issue, but you help the next reviewer, and it's just better for review to understand what's happening. Yeah, but it also has it detects various, so at least the security issues, vulnerabilities, and hotspots. And how does it do this? It has some kind of input. Again, we have talked about this vulnerability and weakness enumerations, and so for the top 10, top 25, it has a mapping. Let's say for, I don't know, injection, SQL injection, or this serialization. This is when you get some kind of some linear bit range, and you convert it back to an object that can be something malicious happening. So basically, for these few elements, for the top 10, top 25, it has some mapping where in the code which kind of functions are doing this, and giving their clear recommendation how to use these functions properly. And if they're not used properly, then you get a bad rating. So what's the security hotspot? Security-sensitive pieces of code that need to be manually revised. Yeah, if it's about authentication, because if you don't do it correctly, then you will break basically the security. I mean, it tells you that it cannot interpret it fully. It cannot give automatically recommendation whether it's correct or wrong. So you should manually look into it, because this is the place where something is happening, but it's really highly important how to configure. So you should take a second and focused look on this. This is a security hotspot. And vulnerabilities, they are well known. So basically, for some of the functions, for the various programming languages, it is known that they can be misused. So for example, I don't know, this, if you create a temp file, make temp, using this specific function is insecure, you should use the other one instead, otherwise this and this can happen. So you get a explanation, but basically it knows that some of the basic functions provided by C or Python or so cause issues, although you can use them, but it recommends to use the safe version of it. So this is a security vulnerability that's highlighted. And again, it's highlighting element. So it's really very similar to the spell checking issue in Word. Duplications can also be listed. Obviously, so why is it relevant? So if you have duplication parts, and that as a such would be technically okay, because it's doing what it should do. But if you modify that code in one part and you forget to modify it somewhere else, then you have an inconsistency. So it's recommended to, if it should exactly do the same, to have one function, put it in there, and if you want to change that function, you change it once, and it consistently changes where it is used. But if you have two copies of the same code and you change only one, then you have an inconsistency that you should avoid. Yes, and obviously then you get also some reports, how much depth you have, reliability and maintainability, security review, vulnerabilities and so on, and you can show how great your software is. And yes, it's not just running on Git servers, so interacting with Git, basically looking at old code, and that has been merged. But it also supports IDE integration. So in your user interface, you get the highlights and the red underlining that you use some kind of vulnerable function. So it supports you in writing clean code, basically also in that part. So basically, you have the Git integrated checks which runs on the code as long as you define, and you have the IDE integrated support where you have this highlighting while you code. So. Okay, yeah, there also you get a rating. So this is the last slide on this. So basically it tells you when you get good rating, maintainability is based on the ratio of the size of the project to the estimated time to fix all outstanding code smells. If you require less than 5% of your time to fix it, then it's A. If you require more than 50%, then it's an E. Security review tells how many of the security hotspots have been checked for the code smells. I'm not really sure whether there's an issue. It just tells the number. Reliability, how many bugs you have. Security, how many vulnerabilities you have, and so on, and you get some kind of rating. So it's helpful to use this kind of tools when you write your distributed system, because obviously it supports you in writing it with less issues, with less vulnerabilities. Okay. So let's say we have passed the threat modeling. We implemented all the recommended security mechanisms. We use static analysis to identify that during the programming we don't use anything unsafe, that we follow the up-to-date recommendations of what methods and functions to use, and now our code is done. So our code is now finished, and now what we want to do is to test the system. So basically here is when dynamic testing comes into play, dynamic analysis. When you run the code, let's say for 20 minutes and check how the memory usage is, the file usage, the CPU usage, and so on. And after 20 minutes you can say, naja, we didn't find anything suspicious. But we want also to look into fuzz testing, as this will be, and this is currently the most effective way to find bugs. So once again, to look into this is just a different view on this. And because, naja, that was the view from Windows, from Microsoft. This is some different view, but it also lists the same elements. Threat modeling are here, ID integration for the coding, static analysis, manual code review, and here we are now at the testing phase. Here's also a slide what shows you what all tools you can have. I mean, we will not go into detail, it's just that there are quite many tools available. So what I want to talk about is to see what the principles behind them are. So let's look into fuzz testing. What is fuzz testing? So fuzzing is very generically said, spoken, it is that you have a program under test. Yeah, it has some input interface, it has some output interface. Yeah, very simple. And what the fuzzing does is to test for bugs automatically in software projects by fully automatedly send millions of inputs and their mutations for days or even weeks into the program and to check, does it give some output or does it crash? It will not verify the output, it will not rerun the program and check what's the result, is it really correct or not, but it checks whether the program crashes. This is easy to see. I mean, then there's some segmentation fault, something is happening. And this is the main feature of it, millions of inputs and their mutations. So basically you have also a rule how to create new inputs. And while with unit tests, let's say you write 100 unit tests for your function and you verify that these 100 tests are working, you will not test for 100 for millions of inputs. Yes, and the idea is, okay, you have this program and a test. This might be located in some Git. Yeah, and this fuzzer is then also integrated in Git. It interacts with it, it runs the code, and it sends it input. If there's an output, you send a new input. If there's an output, you send a new input. If there's a crash, you put that input that you found and the crash report in some file, and then you send more inputs. So basically, over the time, if you give it days or weeks or hours, you compile a list of inputs that cause the crash, and you have the log that describes the crash. It's enforced also to be used by various industries. There's also an open source fuzzing project by Google. Basically, what it is, if you are selected, so open source tools that are hosted on GitLab or GitHub or so, and they are accredited and get this support by Google, then Google is offering its computing power to fuzz the program for a very long time. And basically it has found lots of bugs through that approach. And this is from some conference 2020, they did a study on where bugs are found. So penetration testing actively by some clever people looking for bugs, 24%, code review, 19% only. And even with, I'm not sure whether static analysis has been a thing at that time, but fuzzing, 57%, this is just overwhelming. So this is the best way to find bugs in code that you have. So for example, if I remember correctly, for browsers, Firefox was the example. So typically, so how did they find bugs in Firefox? I think typically you start what you enter, I don't know, let's say Bingen. So this is a typical input that you give for your browser, and then you expect as an output the website to be loaded. So what happens if you start with, I don't know, with some kind of brackets and something like this? Then your system your browser might act differently. So will it, because it expects maybe an HTTP or some kind of description, but what if you start with Unicodes, I don't know, an Ü with long tails? So is it really interpreted correctly? Is it detected as nonsensical and it's rejecting the input, or is it trying to interpret it and make something out of it? So, and you typically would not test for such kind of input for URLs or malformed URLs that you pass on, and then, or what if you enter, I don't know, I mean, there are so many characters that you can pass on to that field which URL you want to load, that if you have lots of time and you give millions of inputs, then obviously you might detect some which trigger an effect which are not handled by the program, and that might then show you that the program crashes because it could not handle the input correctly. So how's the idea? How's fuzzing working? So this is the setup. What do we have? Here we have the code. So here we have the program, the executable. Here's the input. Here's the this is the output, and this is the input. So how do we start? So first we take some initial seed corpus. That is the starting input values. Then we pick one of these inputs. We mutate it, so maybe we add a further character, so we add a +z or +1, or I mean, what is the mutation? You add a letter, you change a letter, you reduce a letter. I think that's almost it. You swap letters. It's very simple. So you get some kind of mutated new seed. And then you give it as an input, and then you check, okay, is the output there? So has it been somehow, did it change something? Did something happen? So did it crash? That would be the success story for the fuzzer. And you feedback the input depending on whether the input led to interesting results into your seed corpus as well. So basically, here you start with, let's say, 5 inputs. Many fuzzers, you would be surprised what they start with. So if you have, for example, a text-based input generator, what would you start with? So if you, let's say, for the browser, want to give an URL as an input, what would be your starting string? No, it's even, either it's empty, so empty string, and then the mutation would eventually add one character more, or you start with A. Yeah, so simple. And you have very few elements there. And if you have a program which accepts an image, then maybe you have an empty image, but with the correct syntax of the PNG, maybe or one white pixel image, but it follows the PNG setup, let's say. So it starts with really very simple input, because the mutation engine anyway has sufficient time to make millions of mutations. It adds a character, it takes a character away, it swaps a character, so 2 characters. And by adding and taking away a character, you can that's already a full complete grammar that you can create any kind of input. Yeah, and okay. So that's it. And with million tries, you create any kind of word. So, and there are various kind of fuzzing elements. I mean, the question is, what is interesting? What kind of additional information do you get about the impact of the input in order to make you decide whether it's interesting or not? And this is where the various fuzzing types come into play. So there's white box fuzzing, which we will not go further into it. That tells you which parts of the code you really are currently executed. That's like when you debug. There's black box fuzzing, when you don't learn anything about the internals of the code. And there's gray box fuzzing. Gray box fuzzing is basically the idea that if you have a code, yeah, this is your code in machine code, yeah, with the different codes. Sorry, this is your input, and this is your code. And basically, if you have in your code various if statements or loops, every time they are basically the potential flow of the code splits. Yeah, if you have an if true, then the left branch, if false, then the right branch, and that might leave you to different parts in the code. Yeah, and the gray box fuzzers gain the knowledge in addition. So if you run your code with specific compilers that gives us an output where you are currently in the code, you can learn which parts in the code you covered. Yeah, in which function you are now. So basically you can draw some kind of map showing which parts of the code you already covered and which not. And of course it's then more interesting to say that if we increase the coverage, so we have now an input that reached new points, new functions, that's interesting, so we should do more of that. So the aim is to increase the coverage of your code, of your input, to as far as possible, so that you, at the end, with your various inputs, have gone through all parts of the code. And everything that increases this coverage, that increases the horizon of the covered code, is of course more interesting, and that you put into your new into your seed basic seed set where you select from to mutate. So gray box means compiled with specific compile flags, allows you to track position of the execution. Where are we currently with the input? In contrast to black box, in black box we don't see anything where we are currently. In white box we would also see a little bit more. Basically it's like debugging where you have the clear source code, and gray box is somehow more doable and gives us sufficient information. So the idea is now, so what is the next step? So basically that already is sufficient, so that you invest more that you say for 24 hours, every time my code has been checked in, I would like to test it for bugs. Okay, so let's sketch out, if this is your code and you added something more, yeah, this is the new submitted code, and the 24 hours are invested to reach out to the whole code and identify bugs. The next time you check in something, the 24 hours are invested here again. Then again a new commit, and as you see, now we have this part has now been checked 24, so basically if it makes, I don't know, 90%, 95% of the code, so this time we have invested here so much time. Here we have, let's say in the first, I don't know, 3 times 0.5 hours, here only 0.5 hours. So the new code has experienced quite less focus, and the old code that has been already checked several times with sufficient time is getting more and every time quite a large share of the focus of the fuzzing time. So what we actually want to do is, because if we take some kind of what do you expect? Where are new vulnerabilities and issues in code? In the part that has already been checked 1,000 times, are here the vulnerabilities more probable, or is here the vulnerability more probable which has not been checked up front? Obviously, if you look at the old code, let's say in the beginning it has lots of vulnerabilities, but then the errors in the old code, they go down. And the errors in the new code, they start at this point. So the longer you have invested in running fuzzing on code, obviously it will detect more and more, has the chance to detect more and more bugs. And over time, when it has been checked already 1,000 times, the probability that there are still bugs is small, whereas new code has a high probability to have bugs. So as a next step, there's the so-called directed gray box fuzzing. So what here the focus is if you give it 24 hours to fuzz, because it costs money to run computations, you want to focus. You don't want the time to be wasted scanning old code. Obviously, also in historic examples, OpenSSL has lots of code, but for new vulnerabilities are introduced in new parts of code, obviously. So you want to focus your fuzzing time proportionally more to the new part. So fuzzers should focus on new part, and the aim is to maximize code coverage of potential buggy new region through selecting a suitable seed corpus. So what you want to do is, if this is the old code and you get the new part, then let's say 90% should go into this of your fuzzing time, and 10% should go into the old fuzzing time for old code. So how can you do this? Again, think of it as a kind of tree structure that we have, and let's say this is the part where your new code is. So you want to quickly focus your code into that area. You want to direct the gray box fuzzing into the new areas. Find input that reaches dedicated points in code, because the new code has the bugs. So what is the idea? The idea is, if you perform this gray box fuzzing, and you get closer to your destination, then it is interesting. Then you give it you give it a higher priority, and you say replicate this or mutate this kind of input stronger. And if you go into the wrong direction, then you say this is of less interest, I don't want more mutations of it. So by simply checking where we are in the code and do we get closer to the region that we want, we can direct the development and the mutations into that direction so that we quickly arrive at the new code part. And what is then done, so basically now this is where it's quite common in general, and there are several tools supporting this so that it focuses on your new code. And we have also done some research in this field. So this is basically where the new part comes, which is less common, but basically state of the art in the research, is by making a clever selection for the seed corpus. So as we have discussed, the typical input for the seed selection, if it's text, then it's just the letter A or an empty string. If it's an image, then it's an empty image. So it's very similar. So it's very simple, and every time you start fuzzing your 24 hours, you have to first explore how do I get along in this tree, and you don't have some kind of pre-knowledge. So starting with a generic seed requires to spend time to optimize the seed corpus during the fuzzing time. So you have to learn every time, okay, this is how the tree looks like, this is where I want to go. And because your time is limited, you spend quite some time in building the tree. And actually once you arrive at the dedicated zone, let's say you have already spent 10 hours of your precious 24 hours. So you have less time on this. And if you look at current fuzzing tools, what kind of input they take. So this is, these are all public fuzzing tools. AFLGO from Google and so on. They take generic seeds. memfuzz takes null seeds or empty, or the generic dictionary, I mean very simple words. iJOHN takes the seed containing the letter A as an input. Parmesan takes the single file with a new line as an input, so it's really very dumb. And the idea was here, so what we did, is once you create this kind of knowledge how the tree looks like, you just memorize for various positions in the tree some input, so that the next time you want to go to the one specific branch in the tree, yeah, then you already have some input that leads you here. So you don't need to memorize many inputs, let's say 500 or so, but they are like a map that tells you if you select this input, you get here in the tree, and then you can directly start at basically exploring that region. So this is the idea with the optimized seed corpus. So we created a map of inputs reaching specific points in code, and the next time we know, okay, here is where we want to go, we select input 1, and if we want to, the new code is added here, then we know, okay, this is input X, where we select what we already know, and we have more time in the dedicated region. So how's the idea here? So basically stage 1, this is done once. Ideally we try to reach 100% code coverage to fully understand the tree. And then basically we filter this huge number of inputs that we learned and where they lead to the tree, so that we have, let's say, at the end 1,000 seeds remaining that tell us explicitly for every seed where we arrive in the tree. So if you take input 1, input 2, 3, 4, 5, and so on. So this is done once. This is your map based on the program, based on the code. And then every time you have some kind of new code attached, so let's say the new code is here, then we know, okay, we make a target-oriented seed identifier. We know, okay, based on our whole map, where we have the seeds 1 to 6, we select just 1 because it's just much closer to the dedicated zone we want to go to. And starting with this, we apply the regular fuzzing, and basically we already explore this part because with the input seeds, we are at the right position already. Okay. Yeah, that's actually the idea. And what it leads us to is, let me just see, I think that's the same. Yeah, basically we have once learned offline, one first step is to create a tree and the allocated inputs. And then once we need to have really the new code running, modified program source, then we make a selection which input we take, and yeah, basically then we do the regular fuzzing. And what we also learned is, the question is, so if you have this tree structure again, we looked into how far can you be away. So let's say you have one input here for, so this is input 1 and this is input 2, and you will want to go into this region. How far can you be away? So how many inputs do you want to store? So if you are, let's say, 10% away, or 1% away, 3, 5, and 0.1% away. So what you could do is to select to make the preference, the input selection, which inputs are interesting, based on the closeness. And let's say, so how close are you in comparison to lines of code? 0.1% of code, 1%, 10%, because sometimes if you are too close, you don't reach all potential ways to the goal. So basically we analyzed it. We had some we took some kind of benchmarking set. So there are some publicly available fuzzing benchmarks which operate on existing open source libraries which have had at that time publicly known vulnerabilities, and the goal is to identify these vulnerabilities that are known. Yeah. And so basically, I will not go too much into detail. So it has basically been selected how many bugs do we find, how many seeds do we need, depending on how close we are. So for example, if we want to the target zone a closeness of 0.1%, then we just need 51 seeds in comparison to some kind of competitors. If we want 10% of the seeds closest to it, then it's 2,500. So basically, it allows us to have a small starting seed set, yeah, and then we simulated this in comparison to other fuzzers, and to check does it have an impact on being already close at the new part of the code. And basically, what came out, so this is a benchmarking set, so it compares different kind of best other fuzzers. And what we came out to is basically this is our approach, this distance-based one, and we found 23% out of 34 vulnerabilities in contrast to the benchmarking reference, which only found 14. So just the outcome was we had much more time focusing on the right code in contrast to the benchmarking set. We found more vulnerabilities, and just in general, fuzzing is quite to recommend. So to summarize, if you can, if it's supported by the company you work and you develop, try to use fuzzing. It's just simple to support in GitLab, GitHub, Bitbucket, and what else. It just runs your code. You give it a specific time that it is allowed to use to run it and to test it with inputs. Eventually, you learn where vulnerabilities are. Graybox fuzzing and coverage-based graybox fuzzing helps you to focus your fuzzing time, your precious fuzzing time, on the new code. And yeah, if you have the chance, try to use it and get accustomed to it, because this is the tool that finds vulnerabilities in general. And maybe one last slide on this. What the next step after fuzzing is, because in fuzzing you test just one system, it's just one code, just one input, one output. But the next step is actually to have something like snapshots, such as virtual machine snapshots, where you have a setup of systems in their current states, and you can give different multiple inputs, you check what's the outcome, and then you revert to the initial state, and then you test different other examples again. This is especially used if it's about networks. So for example, if you have I want to focus in on this example. If you have some kind of protocol exchange, let's say we had the example with TLS, where you first have the key exchange, then you have to derive the keys, then you start, after the handshake, the communication. So sometimes you do not want to start at the beginning, you want to complete the first protocol compliant handshake, and then to start with the fuzzing. So this would be also an example where you basically go through the protocol compliance, key exchange, take a snapshot, and then at that point you start fuzzing, so that you check whether you can break it afterwards. And a similar example, this is therefore it's a nice paper, is how with this fuzzing approach and the snapshot, for example, you can come up with speed runs in Mario, Super Mario, where the system learns. So basically what they did is they introduced snapshots, and how far Mario, so let's say every 5 seconds they introduce a snapshot, and then Mario tried to jump over the gaps and on the Goombas and so on. And when it failed, then it was not successful. If it succeeded, then it was an interesting input, and it was mutated. And basically, by creating, and if Mario succeeded to live for 5 more seconds, then a new snapshot was created. And basically for every 5 seconds or 2 seconds or however it was done, it was able to identify the fastest way how to pass that section, the segment of the level. If it failed, then it was reverted in the virtual machine. And then again, it tried with various millions of inputs to go through the level, and once it succeeded, you could segment by segment proceed. And the same can also be applied for uncovering protocol issues, where basically you snapshot, you try out a million ways to break it. Then if you succeeded, you protocol it. If not, then you're still in the protocol and compliant, and then you try it further on. So basically with snapshotting, this is the next step. And taking a snapshot is, in the meanwhile, below 1 second, basically, if you do it correctly. So you can also think about having really lots of inputs as in the fuzzer required. So this is the last slide with regard also to secure software development. So basically, we are through the topics, and what I recommend you for learning for the exam is go through the slides, see what kind of topics we had. So in this case, for secure software development, we had the threat libraries, the threat modeling, static analysis, we had fuzzing. I think that were the majorities, and then try to summarize, always top down. What is the main idea? What are the details? And depending on how many slides we invested in the topic, the more you have to go into detail. So if we had, for example, one topic with, I don't know, 50 slides, so we went very much into in the deep, such as for TLS, then more details should be memorized, obviously, as if we would just have one slide, then it's probably a less important topic. And if you go then top down, starting with what we had as a topics in each chapter, what topics we covered, what we had more detail, this is what I would recommend. I would recommend to create some kind of, to summarize it in your own words on a page of sheet of paper, 1 page, 2 page, maybe 3, and by writing and summarizing in your own words, this is the learning process. Although you will not use it in the exam, but it's still the helpful to have it available. I mean, to create that document and that learning process to use. Do you have any questions? Anything